Before we get into the development of the spreadsheet, I wanted to go through some basic energy calculations, which I'll go through on this page. The International Space Station is located about 400 kilometers or 250 miles above the surface of the Earth. And the orbital speed is 27,600 kilometers per hour, which is about 17,200 miles an hour. So to lift a spacecraft up and dock with the International Space Station, we have to overcome the gravitational energy, and we have to get enough kinetic energy to catch up with it. We used to fly the space shuttle, and a typical mass for that was about 100,000 kilograms or 220,000 pounds. And I just wanted to do a little calculation of, how much energy is required to get the space shuttle up to the International Space Station. So we derived a formula last time that gravitational energy is big G, big M, little m over R minus big G, big M, little m over R plus H, where H is the height above the Earth. So we can plug in the gravitational constant, the mass of the Earth, and the mass of the space shuttle would be 100,000 kilometers. And perform the calculation, we get 3.696 times 10 to the 11th joules. For kinetic energy, it's just 1/2 mv squared. So 1/2 of 100,000, anyway, 2.939 times 10 to the 12th joules. And you should notice right away that the kinetic energy is about 8 times the gravitational energy. So most of the energy that we're going to need from the fuel is going to go into making kinetic energy, and just a little bit is going to go into making gravitational energy. And so this is our total energy required to go up there. Now, if we use the kerosene fuel, I think I have to do this to go down. If we use the kerosene fuel, we get about 10.7 megajoules per kilogram. Of course, the kerosene itself is about 46.6 megajoules per kilogram, but then we have to carry the oxygen, and when you add in the weight of the oxygen, then that drops it to about 10.7. But you can see we would need 309,000 kilograms of fuel to lift this 100,000 kilogram space shuttle. So it requires lots and lots of fuel. And this is such a basic calculation. We're assuming the rocket's 100% efficient, which it will not be. We're assuming that we're only lifting the weight of the space shuttle itself, which when we blast off, we're going to have to lift most of the fuel, and we're going to have to do a lot of acceleration of the fuel too. So it's going to take a lot more than 309,000 kilograms of fuel to lift that space shuttle up there, a lot more. And so the rocket itself ends up being mostly fuel. And when we do the modeling, we're going to have to account for the fact that the mass of the rocket decreases as we burn the fuel. Just a couple of other minor points I wanted to cover as part of this. To do space travel, we have to go really fast. And we're going about 17,000 miles an hour to catch up with the International Space Station. Neptune is about 2.7 billion miles away, and if we could go twice as fast, if we could go 35,000 miles an hour, it would take 8.8 years, just to do exploration around our solar system. And to travel to another galaxy is just pretty much out of the question. It's not possible, probably not possible at all, but certainly not possible with the rocket fuel we're using today. In the last homework assignment, I'm going to have you assume that somehow we have harnessed nuclear fusion, hydrogen fusion, like what happens in the sun. I think that's the most highest energy density fuel that we know of, that exists in nature. Of course, we haven't figured out how to really harness that energy yet. but I'm going to have you assume this super high energy density and see just how fast you could make the spacecraft go. And I'm hoping that you'll work on it a while. I think it's a fairly tough problem, and you may give up, and that's okay. It's just one problem. And the last topic I wanted to discuss was the ideal fuel. And of course, no such fuel exists, though, in nature anywhere. But we do have that E equals mc squared. This would be a fuel that would just convert the whole mass of the fuel into energy. And that would be that the energy released from such a fuel would make a nuclear bomb look like a little firecracker. But the energy density then would be c squared. And I know that some of you be interested in this, and so if you want to explore it a little further and go to the most high energy density fuel we could